Hi everyone, thank you for coming to our presentation. I'm Parvez, I work as software engineer at Meta. I'm working on FBOSS, more specifically on FBOSS agent. I'm here with my colleague, I'll let him introduce himself.
Hi everyone, my name is Midhun Somasundaran. I'm a software engineer in the networking switch software team, FBOSS team.
Okay, thank you. So, what are we going to talk about today? So, I'll be talking a little bit about FBOSS, what FBOSS is, and what are the different software components. A very broad overview of MPLS, what MPLS is, and what are its general applications. Next, we will discuss certain enhancements we did in SAI specifications for MPLS and what motivated those enhancements. Next is FBOSS. As we move towards using more and more SAI in FBOSS, what challenges we faced, and finally, we will discuss a particular use case in Meta's DC network with MPLS. So FBOSS, as the name suggests, is a Facebook open switch system. This is a project which basically predates the name change from Facebook to Meta. So the name is still Facebook open switch system. It's a control plane software system and hardware that powers our data plane. So there are different software subsystems which form FBOSS software. So I have listed only some of them for the space constraints. FBOSS agent, which implements control plane protocols like LSCP, LLDP, and programs the underlying hardware for routing and forwarding. Next, we have a config management services which generate switch-specific, role-specific, hardware-specific configuration. We also have routing protocol implementations such as BGP and OpenR, and then we have a wide range of monitoring tools which gather statistics, perform alerting, and try to remediate. Again, hardware, there are more than what are listed here. Typically wedge 40, wedge 100, wedge 400, and so on. So the SAI enhancements were done for MPLS mainly because we were integrating FBOSS agent with SAI, and this is why I have put this slide, which gives a cross-sectional view of what an FBOSS agent looks like. So on the top, we have a thrift interface, which is preferred interprocess communication mechanism for it's an RPC protocol. This is used by routing daemons and other monitoring tools to program FBOSS agent, and then FBOSS agent itself has internal layers. Software switch at the top in the orange box is platform or hardware independent implementation of various control plane functions, and then it uses an interface called hardware switch. Hardware switch is an abstract interface which software switch expects to be implemented, and it invokes those functions to interact with underlying hardware. SAI switch is one of the implementations of hardware switch, which basically uses SAI API. And SAI API is a switch abstraction interface API, whose implementations come from the same or different vendors and for specific hardwares. So this is again a very, very high level of overview of MPLS. MPLS is multi-protocol label switching. It is an encapsulation protocol where labels or MPLS headers are imposed on packets. And every MPLS label is basically a 32-bit entity which has a TTL, traffic class, and 20-bit logical identifier. But it also has something called bottom of stack bit to identify where does the encapsulation end. And in the MPLS domain, typically the network nodes are programmed to perform operations such as push to impose labels on the incoming packets, swap to transit the packets and terminate the labels or terminate the encapsulation. So again, this is a very general MPLS use cases. There are vast number of applications in which MPLS is used, but we have listed only few. So one of the use cases is tunneling, where if the Ethernet traffic or L2 traffic is tunneled, then it forms pseudo wire or pseudo LAN services, and if of course it can also encapsulate IPv4, IPv6 traffic. One of the use cases virtual private networks, where multiple router instances exists in the network. The another use case that is very interesting is segment routing. So in a typical network, in hop by hop forwarding, every hop takes a decision on how to forward the packet based on its destination address. But segment routing is a kind of a source routing where the source itself programs the instructions in the packet, how it should be forwarded. And in the segment routing, every segment itself is basically an instruction, and MPLS data plane natively implements segment routing. So its segment routing operations are natively represented by MPLS operations such as push, next, and continue. So why SAI in FBOSS? Basically, to provide more portability across ASIC without having to make too many changes in FBOSS code was one of the motivational factors for putting SAI in FBOSS. Also to try out different ASICs and provide code which is more and more open source and more independent of vendor specific SDKs. So when we started working on MPLS in FBOSS with SAI, initial SAI spec did exist for basic MPLS operations such as push, swap, PHP, and POP. But it did not have enough details for implementing complete data plane support in FBOSS. So some of these I have listed, such as how do you load balance a packet which is MPLS, how to filter MPLS packet based on ACL rules, how to treat special MPLS packets such as the packet which is having an expiring TTL, or control plane MPLS packets such as router alert label, how to deal with the TTL and COS of MPLS packet. So MPLS has pipe and uniform mode, where TTL and COS is either different from inner packets, or it's same, or it's it's inherited from inner packet. So those handlings. Other use cases were for our own accounting purposes, such as what happens for if we get an unprogrammed MPLS label, we to detect say control plane programming errors, and how to keep track of number of packets for given MPLS label. So these are some of the SAI spec enhancements we made for MPLS, and I have listed some of these here. I won't go into details of each of them because we have already discussed these in depth in the OCP meetings. When we started working with SAI, it was our first interaction with the SAI community. And while SAI is very, is portable, and but it is very also broad and general, it leaves some room for ambiguity in interpreting for both application writers and library developers. And it is possible that different vendors, different SDK implementations may implement the same functionality using different attributes. This somewhat increases the complexity for application like FBOSS. And while it was fun interacting with the community, but it basically also slowed our internal deployment. So these were some of the challenges we faced in while we adopted SAI. I'll let Midhun discuss specific MPLS use cases now. Yeah.
Thanks, Parvez. So in the second half of the presentation, we are going to look at the MPLS use cases that we have within the Meta data center. We use MPLS outside the data centers in our backbone also, but we are not going to cover that here, like this specifically within the DC. So there are two main use cases for MPLS in Meta data center. One is segment routing. Segment routing, we use segment routing to redistribute traffic between some of the optimal link and suboptimal links, which the suboptimal link may not be, may be underutilized. So this is basically traffic engineering with the help of a controller. This segment routing use case was discussed in a prior OCP summit by one of my colleagues. So we'll not be going deep into the segment routing use case. Instead, we will look at one of the new use case that we have in our data center, which is based on tunneling. So MPLS tunneling allows us to address some of the unique load balancing challenges that virtual IP addresses are bringing into our data centers. So a virtual IP address is an address which is not tied to a single host. So it can be advertised by multiple hosts, as the name suggests. So it's very useful in our data center. Like we use it a lot. It has multiple advantages. One is that it gives you automatic load balancing. Secondly, it avoids the need for discovery. Third, it's easy to manage and more secure. So this slide shows a simplified view of the topology that we are using in the Meta data center. It's not exact because it's the original topology is a three-dimensional topology. I've tried to flatten it out here. So at the bottom layer, we have the rack switches, which are connecting to the various fabric planes. So the fabric switch is the entry point to the fabric plane. And at the next layer, we have the spine switches. And at the last layer in the DC, like we have the aggregation switch. The aggregation switch, as the name suggests, aggregates traffic within all the boxes in the region. So in this example, like we have a single virtual IP address, which is advertised by 4 servers, 2 behind the rack switch 1, 1 behind rack switch 4, and 1 behind rack switch N. So let's see how traffic that is coming to this virtual IP address get handled normally. First, we will look at the inter-DC traffic. This is traffic originating outside the DC. So the traffic enters the DC through the aggregation switch. Now, the aggregation switch will distribute the traffic based on the advertisements that it received for this VIP address. So with a normal ECMP scheme, what would happen here is that the VIP server 4 would get half of the traffic, whereas VIP server 3 would get quarter of the traffic, and VIP server 1 and VIP server 2 will get 1/8 of the traffic each. Of course, this is not ideal, so that's why we enable unequal cost multipath forwarding, or UCMP, in our switches. So UCMP, what it does is it attaches a weight to each of the path. So the weight here is essentially proportional to the number of VIP servers that are behind that port or link. Once you attach a weight to the weight to a path, in the forwarding path, what it does is it would ensure that roughly the traffic, that is the number of flows that are hashed to that link, is roughly proportional to the weight. It's not exact, but on an average, it works. So with this scheme, like we get like around 25% of traffic roughly on all the VIP servers. Now, let's look at the intra-DC traffic. Essentially, any VIP traffic that is coming, that is locally produced in the region uh, to the same VIP, how it would get handled. Imagine we have a VIP client on racks below the rack switch 3, attached to the rack switch 3. And then any traffic that this client produces would get routed to the server, VIP server 3. This is essentially because we are using shortest path forwarding. So any traffic that is coming from this rack switch 3 would completely ignore the capacity that is available under the other 3 servers, like under the rack switches 1 and rack switch n, because they are not optimal, right? So as you can imagine, this would lead to, like, if with a single machine, it might be okay. But if you have, like, with a single machine, you might be okay. But if you have a number of machines that are producing this VIP client traffic, then it can lead to server overload on some of these machines. And underutilization on the other servers. So essentially, the service can experience some degradation if the amount of traffic that the VIP server 3 in this case attracts is more than what it can handle. So the problem here is essentially twofold. One is that you have the obvious load balancing issue here. Even though you have capacity, you are not utilizing it completely. The second issue is an operational problem. So every time we spin up, we provision a new VIP server for an existing VIP address, we need to be careful where to place it physically. Like if we just spin up the server at any random location, what might happen is that it will start attracting all the traffic that is physically close to it, and it might end up attracting more traffic than it can handle, and it can bring down the service. So a new VIP server commissioning is supposed to increase the availability of the service, but it can have the opposite effect. We have seen in our production DCs instances where spinning up new servers actually brought down the service. This increases the complexity for provisioning tools. Now, the provisioning tool needs to keep track of the physical location of all the servers, and every time a new provisioning request comes in, the tool needs to identify a location which will not cause this kind of overload. So this greatly increases the operational complexity. A similar thing happens when a server goes down also. A very similar thing can happen. So what's the solution that we came up with for this one? It's built upon the solution that we have for the inter-DC traffic. So essentially, if we can take all this VIP traffic all the way to the aggregation switch, the aggregation switches know how to properly distribute this traffic. So we use MPLS tunneling to achieve this. So, so what we essentially do is we used policy-based routing on the rack switch layer to identify all traffic that is coming to this VIP address. And then we tunnel this traffic all the way to the aggregation switch using MPLS. So the fabric switch, the spine switch, rack switch, all of them are doing MPLS forwarding with the VIP traffic in this case. The rack switch will be doing a MPLS push operation. The fabric switch would do a MPLS swap operation. The spine switch would do a PHP operation where it would actually strip off the label and forward an IP packet to the aggregation switch. The aggregation switch would do a regular IP lookup, just like how it handled the traffic coming from the other regions. and the IP lookup will result in a forwarding path which has UCMP enabled, which would ultimately take it us to the correct path. Another thing to note here is that we use something called an Anycast label here. So this is a fixed single label that is configured everywhere in the system, everywhere in the network. So this is a static label. This label is configured as a push label on the rack switch, a swap label on the fabric switch, a PHP on the spine switch, and a POP on the aggregation switch in case we get some label traffic on the aggregation switch. So the use of this static label with configuration avoids the need for any control plane for the solution. So that makes it very simple to manage. We just need to use a single label everywhere, just that depending on what layer of the switch you are in, it is set up differently. The use of Anycast label on all this aggregation switch means that we are dealing with a ECMP of MPLS tunnels here rather than a single tunnel. So that way we get load balancing across all the aggregation switches too. So here is a summary of the solution, just as what I explained in the previous slide. There are some potential future applications also that we are exploring. Basically to extend this for some switch originator traffics like S-flow. Because when we send this S-flow records, the collectors are usually virtual addresses. We don't put the actual physical server address there. So they are also subject to the same constraints for load balancing and placements. This can be extended for future like switch originator traffics like S-flow also. Call to action, please share your MPLS use cases so that the community can benefit and learn from each other. The MPLS SAI spec still has like a lot of changes needed to be like at par with what is used in like a regular MPLS forwarding scenario. So please contribute to MPLS iSpec. FBOSS agent code is open sourced at the GitHub location. So if you are interested in knowing more about the FBOSS switch or the FBOSS MPLS implementation, how we test FBOSS, please visit the FBOSS GitHub page. Thank you.
Thank you. We have a couple more minutes for questions.
Thank you, Parvez. Thank you, Midhun.
Hey.
Good presentation. I have two questions. One is, are you using MPBGP to allocate the labels, or is all static?
So we are using static in this solution. It is completely static. In our segment route use case, it is not BGP. It's OpenR that is allocating the labels.
Okay. So if it's static, then why not allocate from the server? I mean the label. Why you are originating the tunnel from the top of rack?
Right. So we don't want to run MPLS on the servers because of the complexity it brings in to the servers. So we are it's a decision to separate out from the server just because we don't want to bring in the additional complexity of running MPLS on the servers. There are a lot of management, like provisioning and operational reasons also involved because these are usually managed by two different teams also.
Okay, got it. All right, thank you.
Thanks for the question.
Hi. I had a couple questions. One is I noticed in your solution you're sending the traffic through the fabric twice, basically, in some cases. So how do you balance the extra loading on the fabric with this solution? Is it scalable, or is it kind of a selective solution for small amounts of traffic?
It is scalable. The VIP traffic is not a majority of the traffic in our data centers, but it is critical traffic. So we want to make sure that we don't end up in a service outage Yeah, so we want to make sure that we don't have an outage, because of server overload. So we are throwing in some network bandwidth resource to
Got
pick
it.
up the server.
That makes sense. Yeah. So it's getting priority. It's getting the first class airplane ticket. The other question is, do you do any network emulation of these kinds of problems? Like, do you have a virtualized network that you can do simulations on?
Yes, we do have emulation. We use emulation to so whenever we come with a new routing scheme or a new forwarding scheme, like UCMP in this case, so we use emulation to see how much benefits it gives. Basically, our benefit is like what is the maximum link utilization that you can see anywhere in the network. So if the link utilization stays low, it means that the solution is more stable, right? So we use emulation for those kind of making those kind of determinations.
Okay, thank you.
Thank you, Parvez, Midhun. Sorry, we're out of time. You can take the questions offline.
Thank you, everyone.